Okay, let's tackle maybe the biggest question there is, where did, everything come from?
Right, it's fundamental.
And today we're doing a deep dive into the science's best answer so far, the Big Bang Theory.
Yeah, and we've got some great material here that really lays out the core concepts and the evidence. So our goal is basically to walk you through what the theory really says.
What it means.
Exactly why scientists are pretty confident about it, but also, importantly, what it doesn't quite explain yet.
Okay, so the absolute nutshell version. Around 13.8 billion years ago, everything we can see, the whole universe, started from this incredibly hot, dense point. A singularity. And the key thing, which always gets me, it wasn't like a bomb going off in space. It was space itself expanding explosively fast, carrying matter and energy with it.
That's such a crucial distinction. It wasn't an explosion into emptiness. It was the expansion of space-time. And this idea, it didn't come out of nowhere.
No, right. It connects back to Einstein.
Exactly. Our source points out its roots in general relativity, which first suggested the universe wasn't static. Then you had Georges Lemaitre proposing this primeval atom idea.
A cosmic egg, sort of.
Kind of, yeah. But then came the proof, or the strong evidence. Edwin Hubble, 1929, his observations.
Hubble, showing that the galaxies are moving away from us.
And not just moving away, but the further they are, the faster they recede. That's the key observation. It fits perfectly with this idea of space itself stretching.
Okay, so Hubble locks down the expansion part. That's huge.
Yeah.
But the theory also says it started hot and dense. What evidence backs that up? What points to that initial state?
Right. Well, the really compelling piece is the cosmic microwave background, the CMBR.
The afterglow.
Precisely. Discovered almost by accident by Penzias and Wilson back in '65.
Yeah.
It's like fossil radiation left over from when the universe was only about 380,000 years old.
Wow.
And it had just cooled enough for light to travel freely, for atoms to form. But here's the clincher. This radiation is incredibly uniform across the sky. And it has a perfect thermal blackbody spectrum, peaking at a temperature of just 2.7 Kelvin above absolute zero. That specific signature. It's exactly what the Big Bang model predicted would be left over from that hot early phase. It's really, really hard to explain any other way.
So finding the CMBR was like hearing the echo of the Big Bang itself, confirmation of that heat.
You could definitely see it that way. And the tiny, tiny temperature fluctuations in it even give us clues about how structures like galaxies eventually formed, seeds of structure.
Okay, so CMBR is huge. What else is there more?
Oh, definitely. Another major pillar is the amount of the light elements we see out there, hydrogen, helium, and a little bit of lithium.
The basic building blocks.
Right. The Big Bang model predicts that in the first few minutes, conditions were so hot and dense, it was like a universe-sized fusion reactor.
Okay.
Protons and neutrons fuse to form these light elements in very specific ratios. The theory calculates we should end up with about, 75% hydrogen, 25% helium by mass.
And is that what we see?
It's almost exactly what we observe everywhere we look. Stars make helium too, of course, but they can't explain this universal abundance, the specific ratio, starting from scratch. It really points back to the initial unique environment of the Big Bang's first few minutes. The numbers just match up beautifully.
Wow. So Hubble's expansion, the CMBR afterglow with its specific temperature, and the universe's basic chemical recipe, it all seems to line up with this picture of evolving from that initial hot, dense state.
It builds a very strong case. Yeah, the Big Bang provides this really robust framework for understanding cosmic history after that initial moment.
After being the key word there, maybe. Because the source material does mention limitations.
Absolutely. And it's important to be clear about that. The theory describes the universe's evolution from that singularity.
But not the singularity itself.
Exactly. It doesn't tell us what the singularity was or what caused it. Physics, as we know it, kind of breaks down at that point. It can't really address if there was a before the Big Bang.
So it's a boundary to our current understanding.
Pretty much. And it also doesn't fully explain on its own how the universe got its large-scale structure. The galaxies clustering into these vast filaments and sheets with voids in between.
Right. I've heard about inflation theory trying to patch some of that.
Yes, inflation is a leading idea, this incredibly rapid expansion phase right at the very beginning, fractions of a second in. It helps explain the smoothness of the CMBR and potentially how those initial seeds for structure formed. It's an extension to the basic Big Bang model.
Okay, so summing up then.
Okay.
The Big Bang theory isn't really about the bang itself, but everything that came after. It gives us this powerful, evidence-backed story of expansion, cooling, forming the first elements. Basically, the universe's evolution.
That's a great way to put it. It's our best model for the universe's history and evolution. Absolutely essential for understanding, well, our place in the cosmos and the physics governing it all.
So thinking about this, if the Big Bang describes the evolution so well, explaining how we got from point A to now, what does it really mean that the theory itself hits a wall at point A, at the origin of that singularity? What questions does that leave you thinking about regarding the ultimate beginning? Something to ponder.